All right, yeah, I believe I can start, otherwise we already were slightly delayed, so let me begin. So we ended at this note that if a subset is not passing through the origin, then it's not going to be a subspace. In other words, for subspace, it is mandatory that zero vector or the origin is basically part of the subspace, right? So let's look at talk about the dimension of images, those MNIST images that we saw earlier. As if we understand it as a linear span, then what does it mean in terms of dimension? So if you remember, we had this image of 0, and here the black is basically 0 and white kind of means a 1 or 255. That's the RGB scale. And so if you remember, what we were saying is, the third row and the seventh column is 29, third row, eighth column is 254, third row, ninth column is 32, and so on. So you can enumerate all the non-black pixels out. And when you enumerate all the non-black pixels out, then you may kind of question, how many non-black pixels can I have in an image like this? The answer is, at most you will have 14 by 14 or 196 pixels. So that becomes the dimension of these kind of images. Now once again, remember that original MNIST is not 14 by 14 but 28 by 28. So that will have a dimension of 28 times 28, which is 784. So that's the dimension of an MNIST image. So what's the notation or convention that we'll be using? So each vector has a coordinate representation in a basis. And once again, once I fix the basis, the coordinate representation becomes unique. So you want to think of this coordinate representation to be unique. Then there is a set of vectors v1 to vn, which is basis of some vector space or subspace. For example, it could be the set of images, or it could be the set of a subset of m-dimensional real space, and so on. And then any vector v in the vector subspace will have therefore a unique coordinate, which is a column vector, and that's what this transpose T here means. So it's a column vector a1 to an. These coordinates are with respect to a basis. So every time you kind of see a coordinate of a vector, then the basis has to be specified. If the basis is not known, the coordinates are not known as well. So whenever we talk of v vector as a1 to an, the basis is implicit or assumed to be kind of known. Now you may say, like, is there some advantage in changing the basis? We'll see one example shortly. So but before we get there, I want to kind of cover this idea of inner products, often called as dot product and so on. So if we have, let's say, two vectors in and some n-dimensional space. So let's say v vector has a coordinate representation a1 to an, and w vector has another coordinate representation b1 to bn, and we are assuming that these so we are assuming that the basis is known, so that we can write this coordinate representation. Then their standard inner product. I mean, inner product is actually more general than what is written on this slide here, but this is the one that is kind of widely used through engineering. So the standard inner product is you just kind of multiply, coordinate by coordinate. So a1 times b1 plus a2 times b2 and so on, and then kind of add it all up. Right, so you just take a1 b1 plus a2 b2 all the way up to an times bn. Now once again, there are other inner products too, but for data processing, I mean, typically the standard one is the most commonly studied in practice. So let's look at, so there would be a technique called principal component analysis, or PCA. We'll kind of get there. So let's go back to the that digit 0 from the MNIST data set. So this is how it may look like. I think it's probably the transpose of it. So this is 28 pixel by 28 pixel. And so these check boxes that you kind of see, or checkered boxes that you see, that kind of tells you how many pixels are there. So now because it's 28 by 28 pixel wide, and each pixel can have a unique non-zero value. So therefore it has a dimension of 784. That's 28 times 28 or 784. So we'll say that there are 784 vectors, q1, q2 all the way up to q784, which will kind of appear as a basis for these kind of images. Now where exactly is this q1, q2 and so on coming from? So how do I get these basis function? That we'll cover later. Okay, so that's what I mean by it is known using principal component analysis, or PCA. But this is just to kind of give you a glimpse into why should I care about basis. All right, should I not? So for example, if you go back here, when we first saw this image, we had this as the basis, right? And you may think that, okay, if I have one basis, then maybe it's good enough. So the question comes, I mean, does it make sense to kind of think about other bases or not? And the answer is yes, and that's what I'm going to kind of tell you. All right, so why should I think about some other basis? So there is another basis that you can obtain using PCAs, and this basis would not be that vector that I discussed, which was 1 in one non-zero pixel and 0 elsewhere. That's how we had constructed the canonical basis in the pixel dimension, right? So if you don't use that, then it turns out that you can create a new basis set Q1 to Q784, such that if I look at this image 0, and I start looking at its coordinate, the coordinate would be 784 dimensional, right? Because there are 784 vectors, so there would be 784 coordinates of this image. That's not surprising because the image has 784 pixels. But what is surprising is the following. So if I start looking at inner product of this image of 0, which is what x vector here is, and each qi that we have, then you would see that the coordinates decrease very rapidly towards 0. All right. So this I here is the the index of these basis vectors. It's contained till 250. I mean, it can be taken further, but this is just to kind of illustrate a point that even though the first coordinate is as large as 1200 or 1300, very soon, like let's say around I equal to 250, you see that the coordinates are not even equal to 100. They are much smaller. So the coordinates decay rapidly towards 0 in this plot here. One can even see these. So whenever you see a graph kind of hitting 0, it's illustrative or instructive to look at it in log scale. So one can also look at this in the log scale, and then you kind of see the same thing, right? There are few coordinates which are like really small. Even in the log scale, these are like e to the power minus 4, while the central or the dominant coefficients are as large as e to the power 6. So there is like a 3 or 4 orders of magnitude difference between the coordinate here and the coordinate here. Can I use this decay of coordinates somehow? And if I can, then it justifies that it makes sense to have an alternate basis. Okay. So you can do what is often called as compression with PCA. So you can use it to compress the image, and this is how you do it. So if I want to have an ideal or lossless representation of this image here, then I need 784 coordinates or pixels, right? If I can just I can encode each pixel separately using a scalar from 0 to 255, and I can get this losslessly. There is no loss whatsoever, right? And that's lossless encoding, but it comes at the cost of recording 784 coordinates. Okay. So if I look at this, the PCA basis that I had, or in general, I can kind of pick any basis of 784 dimension, and then I can start representing this image using that. But if I do it using this PCA basis that I have, what I can do is I can truncate the formula somewhere, right? So the way we obtain the coordinates of x vector along these vectors is by taking inner product. So I'll take x vector, I'll take its inner product with q1. That gives me the coordinate of x vector along q1. Similarly, I'll take x vector, take its inner product along q2 vector. That gives me its coordinate along the q2 vector, and so on. So what you do is you come up with this k-term approximation. So take the inner product of x vector along with q1, along with q2, all the way up till along with qk, and then resynthesize. So this is x vector hat, it's not x vector. The hat is like way up here, but so this is happening because I converted from Keynote to PDF or whatever. So just think of this x vector as an approximation. So this is k-term approximation of x vector using q1 to qk. Now if k was taken to be n, which is 784, then I'll get it back losslessly. I'll have no loss whatsoever. On the other hand, if I select k to be smaller, then I will have some loss, but I may be able to save on how many coordinates do I need to collect. And if you see this image here, this is with k equal to 100. So what this is showing is that, well, a 0 can be obtained approximately as a 0. It's not the same as what you had here, but it still looks approximately as a 0, even though I have only collected 100 coordinates. So if I go back to this plot, if I stop the coordinate collection along Q1 to Q100, and I kind of ignore all these things. If I ignore all these tail part of the coordinates, I'll get this approximation. All right. So PCA, for example, can be used to compress the vector that you have. And that's where actually the name is also coming from, right? Principal components. So the whole idea is like that you think of these components as being principal, the larger ones, because those are the larger ones. They are going to define what the image actually looks like. And these are not the principal components. In other words, they are going to add fine details to the image. They are not going to be the dominant one, defining characteristic. They are just going to have, they are going to add fine details onto this shape so that it kind of begins to look like this. You can even compress other digits. So for example, I can take a digit 1. I mean, this doesn't look like a 1, but imagine, lots of people writing 1 with varied strokes. So some of the 1 may look like this. And again, if I want an ideal or a lossless representation, then I need to have 784 coordinates or scalars. But if I only collect 50 coordinates, I'll get this kind of approximation. Looks a bit blurry, not super, but if I go towards, let's say, k equal to 200, this is 200 point approximation, about 4 times compression is there. And it's very difficult to tell whether this one is the original or this is the lossy one or the vice versa, right? I think some of it is happening because of the lighting also. I think, yeah, this light is shining on this, but this is darker than this.
So the principle is that we try and identify the
So the principle is that we try and identify the significant part of the.
Yes. So the whole idea is like principle means that which are the largest coordinates that I should be collecting. And if you collect more and more coordinates, yes, your representation will get better and better.
And we could negate the rest and we could just ignore the rest.
So you would ignore so that you get compression. So if you care about compression, basically you can have a trade-off between how much can I compress and how much loss I have. If I'm going after lossless representation, then I know that I have to have 784 pixels. There is no other way around it. But let's say I'm willing to sacrifice half of the coordinates. So if I'm willing to, let's say, do 392 point representation, can I do it? And if yes, then how much error will I have? So those kind of things are answered by PCA. There was another question. Yes.
Please go to the previous. Then what is X here, sir? I didn't get that.
X vector is this image. So I'm thinking of this image as a vector. So what you can do is, this is basically 2-dimensional. So what you can do is you can just look at the first row and then the second row and kind of stack it together. So you'll get a 784 length vector.
Okay.
And
if you took the under image, then probably, I mean, for example, if there are under image, the 0 is nearer to the top. Okay. Then obviously the total studies will be differ.
sorry, total?
I mean, if the 0, probably this 0 is middle of that picture. Okay. If the 0 is in the top or bottom of the picture, then how to do the things?
It's the same because we are dealing with 28 by 20, so you don't have to bother about whether the 0 is towards the top or towards the bottom. I think the PCA, I haven't told you how these vectors are learned, right? Once I tell that, maybe that would be clearer. But for now, just assume that there is some way to learn these. And it so happens that for this particular image, if I use this particular basis, I see a decrease in coordinate. That's the only thing I'm telling. So I'm just telling you a story that something like this would happen in the future. I haven't told you how it has happened. Okay, so is that clear? So the scope of the example is that it kind of makes you curious that apart from the canonical basis, which was basically 1 pixel non-zero at a time, I can have some smarter basis functions which give me some desirable properties like compression. Yes, there was a question. I is the index or the number of coordinates that I am willing to collect. So along with I, the coordinate of X, which is basically this image, is decreasing. So as I add more and more vectors from the the basis of PCA, I see that the coordinate of this particular image is decreasing.
But how it will be decaying rapidly, sir, with respective in
so that is by so basically that comes from the design methodology, like the way we obtain Q1 to Q784. The answer to that lies in how have we designed these vectors. These vectors, it turns out, will depend on the type of images that we are using. So it's a custom built
Custom.
Orthonormal basis. How it is done, again, I will
No.
once again, we'll see that towards the end of this short course. Okay, so once again, the whole motivation was that, it makes sense to think about alternate basis, not just the canonical one, because it may give you some desirable properties like compression and so on. So, for example, this one is having 4 times less amount of data. And so therefore you can process it faster, you can store it in smaller space and so on. Okay. There's also this notion of a normalization of a vector. So given any vector v, I can normalize it to a length of 1, which is u vector. And the way we do it is by, just take v and then divide it by its inner product. So the inner product of v with itself will give you the length square of the vector. So just divide by the length, not the length square, divide it by the length of the vector to get a normalized unit vector. All right, so you can see that here. So v vector is the longer one, and then if I normalize it, I'll get a vector of length 1. Now the vector u will still point in the same direction as v. That's the main part here, right? So u vector is still pointing in the direction of v, but it's going to be of unit length. Okay. Then there's this notion of projection. It so happens that PCA PCA representation is actually obtained by projection, so it's useful to know this. So if I start with a vector v and some other unit vector u, then projection basically just means that take the tip of v vector and kind of drop it in the direction of u. Okay, so that's the geometric description. So I want to take v vector and then drop its tip to the closest point along the direction of u. That's basically called as, and sometimes called as a normal projection, orthonormal projection, or I would kind of just call it as a projection. And it's basically a perpendicular drop from v vector towards this. What does perpendicular drop mean? So once projected, if I draw this line, right? So this line is basically the difference between v vector and the projection. So that's going to be perpendicular to u vector. Okay. So there's this notion of orthogonality that shows up again and again in linear algebra and machine learning. In fact, it shows up in many computational sciences, not just machine learning. So given vector v and w, we had defined that the inner product is a1 times b1 plus a2 times b2 all the way up to an times bn. So if I insist that that is equal to 0, then the vectors are called as orthogonal. So v vector and w vector are orthogonal if their inner product is equal to 0. More than 2 vectors are orthogonal if they are pairwise orthogonal. So if someone gives you 3 vectors and asks whether they are orthogonal, then those 3 vectors will lead to 3 different pairs, right? And so you have to check whether all the 3 pairs are orthogonal. If someone gives you 4 vectors and asks you if it is orthogonal, then 4 vectors can lead to 6 pairs, right? 4 choose 2. So you have to check orthogonality on all those 6 pairs. All right, so orthogonal vectors will form a basis for a subspace. All right, so orthogonal vectors are always linearly independent. So they will form a basis for a subspace, and the dimension of the subspace will be equal to the number of orthogonal vectors that we have. Then any basis can be transformed into an orthogonal basis by what is called as a linear transformation. So you can just do linear operations or linear combination operations on a basis, and that will lead you eventually to an orthogonal basis. All right, again, this is canonical from linear algebra point of view. If you have doubts, feel free to ask me after the class, but this I am assuming that you would have seen it. It's just as a recap. Similarly, orthogonal vectors can each be normalized to length 1. So you take orthogonal vectors and you divide it by its length, so that you get orthogonal vectors which are of unit length. And so these are called as normalized orthogonal vectors, often called as orthonormal vectors. Instead of normalized orthogonal, we just call them as orthonormal vectors, and that leads to what is called as an orthonormal basis. So it turns out the PCA basis that we saw before, that happens to be, so this PCA basis that we are talking about, that happens to be an orthonormal basis. So there's also this notion of orthogonal projection. So earlier we saw projection along one direction, right? So now let's look at projection of a vector along a subspace. All right. So instead of projection of a vector along one unit vector, we will look at projection of a vector along a subspace. So let us say we have u1, u2, u3, and so on up till uk. So these are some orthonormal vectors that we have. they form a subspace that's depicted by this plane, right? So it's hard to draw like k-dimensional pictures, right? Beyond 3 dimensions it's hard. So just imagine that all these u1, u2, u3, all these are perpendicular to each other. And what we want to do is we want to take a vector v, which is not in this subspace, it's outside the subspace, but we want to kind of drop it to some closest point in this subspace. All right, so that's the whole idea here. So I want to figure out a v projection corresponding to each v, such that v projection lies in this subspace. All right, this subspace which is spanned by orthonormal vectors u1, u2, u3, and so on. Okay, so the way it is defined is, you can define v projection to be the inner product of v, or basically the projection of v along u1 and then multiplied by u1, something that we have just seen before in that PCA approximation formula. So this is inner product of v with along the direction of u1 and then multiplied by u1, right? So that's basically the component of v vector along u1. Then add the component of v along u2 and so on. Keep doing it till you have component of v along uk. Add it all up and then you get the projection of v vector in this subspace. But that's not how a projection is defined, by the way. The way projection is defined is that you want v vector minus v projections. That's the error vector. You want the error vector to be perpendicular to this entire subspace. So this formula is obtained from that description that you want the v projection. So v projection is going to be a linear combination of all these vectors u1 to uk because it's in that subspace. All right, so that's where we get this linear representation for v vector, v projection. And then what we want is that the error between v vector and v projection, that should be perpendicular to the entire subspace, which eventually means that it should be perpendicular to u1, should be perpendicular to u2, all the way up to it should be perpendicular to uk. So this gives us that the coordinate of v projection, which v projection along u1, which is a1, that's going to be the inner product between v and u1, and so on. So you can derive this. Again, this is a classical result from linear algebra. All right. There's also this notion of eigenvectors and eigenvalues that shows up again and again, and all these things will kind of combine very naturally into the whole PCA algorithm, as you will see later. So for a given square matrix A of size n by n, so we are assuming that we have a square matrix, otherwise eigenpairs are not really defined. So so we are looking at a square matrix of size n by n. An eigenpair basically means it's a eigenvector and eigenvalue kind of going together. That's what an eigenpair means. So so for a matrix A, x vector is an eigenvector. If I apply A on x vector, then all that it does is kind of changes the length of x vector. That's what eigenpair or eigenvector means. So here A is the lambda is the eigenvalue and x vector is the eigenvector. The other thing that we require is that x vector should not be 0, because if x vector is 0, then this is trivially satisfied. So when we seek eigenvectors, then we want the eigenvectors to be non-zero, strictly non-zero. So once again, if A is like a matrix, right? So it's multiplying, it's like a linear map. So what we are insisting is that if I apply A on x vector, then x vector just gets scaled by lambda. All right, when I apply A on x vector. And there's this notion of spectral decomposition. So this may be slightly new for you. So so there's this notion of spectral decomposition. So spectrum, you may wonder like what does spectrum mean when it comes to matrices. So spectrum corresponds to the eigenvalues. So the eigenvalues are often called as spectrum of a matrix, and therefore eigenvectors becomes the the vectors along the or often called as spectral dimensions or spectral vectors of a matrix. All right. So we have A times x vector equal to lambda times x vector. So that's the definition of eigenvectors. So the following things are known about a symmetric matrix. So what does symmetric matrix means? If I look at transpose of A, then that's the same as the matrix A itself, right? So if A is equal to A transpose, we call it as a symmetric matrix. So the following things are known about symmetric matrices. One, all the eigenvalues of A are real. All right. So A will have n eigenvalues and all of them are going to be real valued. So typically we obtain eigenvectors by solving a polynomial equation. We know that polynomial equations may have complex roots, and that's why this result is non-trivial, because it says that if you have a symmetric matrix A, then it's polynomial, then the corresponding polynomial equation which gives me the eigenvalues, that will only have real roots. Okay. The other thing that we know is that the eigenvectors of A will form a set of orthogonal vectors. All right. So not only we know that all the eigenvalues of A are real, we also know that its eigenvectors are going to be orthogonal if they correspond to different eigenvalues of A. So if I have, let's say, n distinct eigenvalues, then I know that I will have n distinct orthogonal eigenvectors. Now, if let's say one eigenvalue is repeated, let's say for example, the eigenvalue 1 was repeated, so I have two eigenvectors corresponding to lambda equal to 1. So then you can form a set, meaning you can, you can take those two eigenvectors and you can orthogonalize them. And that's what this statement 2 kind of means. So that eigenvectors of A form a set or can be made to form a set of orthogonal vectors spanning the entire n-dimensional space Rn. This is true for any symmetric matrix, by the way, any symmetric matrix A which has real valued entries. Now, because you have orthogonal eigenvectors, so you can normalize them, and therefore the eigenvectors of A can be made orthonormal. So for any symmetric matrix A, you will have an orthonormal set of eigenvectors, and that's a very powerful result. If you have any time tried deriving eigenvectors for square matrices, you would have noticed that many times you don't get a complete set of eigenvectors also, and so therefore it's surprising that you will end up with an orthonormal set of eigenvectors, and all that happens just because you are looking at a symmetric matrix. Now let us say that lambda 1 to lambda n, yeah, this should be lambda n. So let us say lambda 1 to lambda n are the eigenvalues, and corresponding eigenvectors are u1 to un. Then the matrix A can be written as in this particular form. So if you observe here carefully, this is basically the eigenvector u1. So it's not u1 transpose u, which is what we are used to, right? Like, so that's basically the inner product. Here we are looking at u1 times u1 transpose. So it's often called as the outer product as opposed to inner product. And u1, if you remember, was a column vector, so that's n by 1. So if I look at u1 transpose, that's going to be n by 1 times 1 by n. That's basically n by n matrix. So if I add n different n by n matrices scaled by appropriate eigenvalues lambda 1 to lambda n, then I can get back the matrix A. And that's so this decomposition is again very central in many areas of again computational engineering as well as electrical engineering and so on. Finally, one can also write this matrix A as this expression Q times lambda. Lambda is a diagonal matrix corresponding to eigenvalue times Q transpose. Now, what is the special property here? So the special property is that if I look at Q times Q transpose, that's identity, which means Q is a normal matrix. So Q has basically orthonormal columns as well as orthonormal rows. So if we continue to the main idea here, so the matrix A can be written as Q lambda times Q transpose, where Q has columns which are orthonormal, and not very surprisingly, the columns of Q are nothing but the eigenvectors of the matrix A here. So let me actually just explain this in a minute. Yeah, maybe I should have. So I have this matrix Q, but before that we had, let's say, symmetric matrix A, right? So A was such that A is equal to A transpose. This leads us to n orthonormal eigenvectors. Correspondingly, we have n different eigenvalues, right? So that's the decomposition we have here. So you can synthesize A in two ways. One is I can just take these outer products. So there are two types of synthesis we can have. Either I can synthesize by taking outer products of the eigenvectors and then multiplying it by lambda, or alternately we can write the same thing. This same thing can be written as follows. So you define Q to be this matrix. So you kind of collect all the eigenvectors u1 to un, right? So I have n different eigenvectors of dimension n each. So each of this is n by 1. So if I look at this matrix Q, this will become n by 1 associated with or augmented with n by 1 all the way up to n by 1. So this is n by n matrix. And if you see that lambda fellow there, that lambda is a diagonal matrix which consists of all the eigenvalues lambda 1 to lambda n. All right. So that's how you want to kind of picture everything. So there, if you use all this notation, then this representation of A that we have here, that also corresponds to this second representation, that A can be written as Q times lambda times Q transpose. The key thing is that you want to think of Q as, the augmented matrix that you obtain by keeping all the eigenvectors u1, u2 all the way up to un together. Now, these ui's are orthonormal, and that's what gives us this second property, that Q times Q transpose is equal to identity. This also means that Q transpose times Q is also identity, which means basically the rows of this matrix Q, even though we constructed it by augmenting the columns together, but once you do that, it would turn out that even the rows are going to be orthonormal. But the rows are not the eigenvectors, the columns are the eigenvectors of A. Okay? So let's keep this in mind when we get to PCA. We will be using this spectral decomposition part again.